Hello, in this video, we're going to be going over practice problems for the standard normal distribution, which is section 6.1 and 6.2. You should have already viewed the section 6.1 normal distribution PowerPoint and reviewed the first page of your guided notes document. We'll begin on page 2. Our first question, give the reason why each curve is not a normal curve. Take a second and see if you can figure out why each curve is not a normal curve. We can see for part A, the first curve is not bell-shaped. It has two bumps in the middle. Also, on the outside, you can see that the edges go up instead of approaching the x-axis. On the second curve, while we do have a bell-shaped curve, the ends go below your x-axis. For a standard normal curve, we should have a bell shape, but then each tail should approach the x-axis, but never touch it. For the second example, we're reviewing the empirical rule. Remember, the empirical rule says that 68% of your data fall within one standard deviation of your mean. For normal data, 95% of your data fall within two standard deviations of your mean. And for normal data, 99.7% of your data fall within three standard deviations of the mean. So our answer to this question 2, according to the empirical rule, for a distribution that is symmetric and bell-shaped, approximately 99.7% of the data fall within three standard deviations of the mean. For question 3, it says, assuming that the heights of boys in a high school basketball tournament are normally distributed with a mean of 70 inches and standard deviations of 2.5 inches, how many boys in a group of 40 are expected to be taller than 75 inches? I've written out the information we know. The mean is 70, the standard deviation is 2.5. So if our mean is 70, when I add two standard deviations above the mean, I get 75. So 75 is our mean plus 2 standard deviations, or 70 plus 2 times 2.5 equals 75. And we know that two standard deviations above and below our mean, that range, accounts for 95% of our data. So the middle 95% of our data is in this yellow area. So that means the other 5% of the data is split up on the two ends. So I would have 5% divided by 2, or 2.5% of our data is below 65, and 2.5% of our data is above 75. So we can say that there's a 0.25% probability of a boy having a height taller than 75 inches at this basketball tournament. So to find our expected value, we would take our number of items times the probability. So we'll take 40 and we'll multiply it by 2.5%. As a decimal, that's 0.025. And we get 1. We can expect one boy in the group of 40 to be taller than 75 inches. We can also do this problem using our calculators. As you can see in my diagram I've drawn on the right, I've drawn a normal distribution with a mean of 70, and I noted that sigma is 2.5, and then I want to find out the probability of a number being greater than or equal to 75. So I shaded in to the right of 75, so it's greater than, and I wrote P equals question mark, because that's what I'm looking for. To do this using our calculator, we're going to press second vars, which is where we get distributions, and then we're going to choose the second option, which is normal CDF. In our lower limits, you're going to follow your graph until you have the lower bound of your shading, which is at 75. For your upper limits, you need to go at least 4 standard deviations out from the mean, but I usually just like to pick a really high number, so I put 9999. The mean is 70. The standard deviation given in the problem is 2.5, and then you can just go ahead and press paste or enter again, and we get 0.0227. I'm going to say 0.023. Note the 0.023 is slightly off from what we got using our empirical rule, and our empirical rule is an approximation for the data, so that's okay. So what we're going to do now is find our number of items times P, our probability, or 40 times 0.023, and we'll get an answer of 0.92. So we can expect 0.92 players to be above 75 inches. Once again, an approximation. You can't have an actual just portion of a player like that. For question 4, we have X is a random variable representing the length of time it takes a student to complete Dr. Gill's chemistry lab project. From long experience, it's known that X is a normal distribution with a mean mu is 3.6 and the standard deviation sigma is 0.5. We'll use that for both parts of the problem, A through C and D through F. Convert each of the following X intervals into Z intervals. So for the first part here, you'll see I listed to the right our formula for our Z-score. And this is simply practice in plugging into the formula. So I know that for all of these parts, I'm going to have mu is 3.6, sigma is 0.5, and then I'm going to fill in the formula. So for the first one, I'll have Z equals 4.5 minus 3.6 over 0.5. I get 1.8, so I can say Z is greater than or equal to 1.8 when I do that data transformation. The next one, I'm using the same formula, only this time I have to replace 3 first, and I'll get negative 1.2 for Z. That makes sense because 3 is less than the mean of 3.6, so it makes sense to get a negative number. So I know that my Z-score is going to be between negative 1.2 and whatever I get when I put 4 in. So now I'll put 4 in. The Z-score associated with X equals 4 is 0.8. So for part B, we get Z is between negative 1.2 and positive 0.8. You try converting X is less than or equal to 2.5 into a Z-score. You'll get Z is less than or equal to negative 2.2. For the next part, we're converting each of the following Z intervals into raw X scores. So we can use the same formula, only this time we're going to manipulate the formula. So if we have Z equals X minus mu over sigma, first I'm going to multiply both sides of the equation by sigma. And I'll get sigma Z equals X minus mu. That converts to the equation X equals mu plus sigma Z. We're going to use this to fill in our unknowns. So we're going to fill in the equation for the unknowns. We're solving for X, so that's what we're trying to find. And to do that, we'll take the number in each problem and we'll plug it into the box and perform the operations. Go ahead and try that, and then we'll check all 3 answers together. Pause the video. For D, you'll get X is less than or equal to 3.1. For E, you'll get X is between 4.1 to 4.6 inclusive. And for F, you'll get X is greater than or equal to 4.35. Remember, converting to Z-scores transforms the data such that it is centered at 0. For this next example, we're going to use our calculators to help us as we compare the sales for 2 different salesmen in 2 different districts. John and Joel are salesmen in different districts. In John's district, the long-term mean sales is 17,319 each month with a standard deviation of 684. In Joel's district, the mean sales is 21,971 each month with a standard deviation of 495. Sales in both districts follow a normal distribution, so that's important to know. Last month, John sold 19,214 worth of merchandise, so that would be his X value for the problem. And whereas Joel sold 22,718 worth. Convert Joel's last sales month to a standard Z-score and also do the same for John's last sales last month. As you can see, I've written the information we know for each salesperson, and I've written the Z-score formula on each side because that's what we'll need. So we're going to go ahead and fill in those formulas to find our Z-score. Pause the video, try it on your own, and then check with me. You can see John earned 2.77 standard deviations above his monthly mean sales. That's what the Z-score represents. While Joel's Z-score is only 1.51. So While both earned above their monthly means, John's value was more extreme. So in those terms, he had a better month relative to what he usually does. Now we need to find the area under the standard normal curve to the left of Joel's z-score and to the left of John's z-score. So first thing we need to do, we always need to draw a diagram for these types of problems. So it's a normal curve, and we can do this in terms of z-scores or using our original data. So I'm going to do it in terms of z-scores first because we just calculated a z-score. So on this normal curve, we're going to call this x-axis z, and it's centered around 0 because when we're using z-scores, our normal distribution is centered around 0. So that is our mean in that case, and our standard deviation is going to be 1 in this case, and we have a value at 1.51. We want to find the area to the left of that, so that's what I'm going to shade. You can use a z-score chart to do this, or you can put into your calculator normal CDF. Our lower bound, well, looking at this, there really is no lower bound. It continues infinitely in that direction. So you have to pick a number that's at least 4 standard deviations out. So at least -4, but I always like to just pick a really low number like -9999 up to my upper bound where the shading ends at 1.51. Then you have your mean 0 and your standard deviation 1. And remember, we're pressing second vars in order to get to the spot where we see normal CDF. When we do this, we get the area under the curve is 0.934. Now we use z-scores to come up with our answer, but you can actually do this problem without using z-scores. We can clear this axis and make it an x-axis, and then relabel in terms of the values he made before the conversion. It's still a standard normal distribution, but instead of being centered at 0, it's centered at 21,971 with a standard deviation of 495. And we're looking for the area to the left of 22,718. So in our calculator, we'll do second vars again, and we'll type normal CDF. It's still boundless on the lower side, so we'll pick a really low number. I have -9999 up to 22,718. The mean this time is 21,971, and the standard deviation is 495. Go ahead and press enter. Once again, you'll come up with 0.934. If you do a problem like this again, you don't have to convert to the z-score in order to find the area under the curve. You can simply use the numbers given. Now what I'd like you to do is pause the video and go ahead and find the area under the normal curve for John's z-score. Pause the video, we'll meet up in a moment. Here you can see on the left-hand side that using z-scores, you come up with the area to the left as 0.997, but you can also do this problem using the information given in the problem without the z-score conversion, in which case you're still using normal CDF and you still come up with 0.997. And as we talked about before with respect to their districts, who did a better job last month, and that would be John. The area under his curve is greater and his z-score was more extreme. Tune into the next video to see pages 5 and 6 of your notes and learn more about applied problems with the normal distribution.